So I'm very pleased that Richard Davis could find a few days, despite what is an increasingly busy schedule for him, to come and join us at ICP this week. And in particular, he's agreed to give this talk before he has to, unfortunately, dash off back to the States. Yeah. So, Richard, over to you.
Okay. Thanks very much for the introduction. I'd like to thank the organizers for putting on this meeting for this month. I intended to be here for a much longer period than just a few days, so I'm sorry I missed it. I missed most of it. It's great to be back at the Newton Institute. I was looking up this morning when the last time I was here, and it turned out to be 1998. And then I was also curious about what I spoke on. I couldn't remember. And the title is remarkably similar. So in 16 years, it appears that I haven't really changed a whole lot. The title was Asymptotic Theory for some Nonlinear Time Series Models. So you could permute this a bit and it'd be almost the identical thing. It was actually completely different than what I'm going to talk about today. So back then it was about I think it was about Garch processes, but there's going to be something called in-Garch here. So there is a connection. In-Garch here, it refers to integer Garch, and the Garch back in those days was standard Garch. Okay, so this is a topic that I keep coming back to. I started work on this maybe in the mid. Geez, I can't remember now. Happens to you. Probably the mid-90s or so, with some work with William Dunsmuir from UNSW in Australia. And I keep coming back to it and get re-energized every so often. And so this work, this part of the research component was done with Hung Lu, who's a former PhD student of mine at Columbia. He's now at Google in Mountain View. Okay. So here's the game plan, topics I'd like to talk about today. When you model time series of counts, so we're thinking about time series which are discrete valued or take count values, meaning like 0, 1, 2, 3, 4. We're thinking about small numbers, not large integers. And there's typically two frameworks or modeling strategies or types of models that one uses for such data. One is called parameter-driven and the other is observation-driven. These terms were coined by Cox some time ago, and they're not perfect. There's models that kind of fall through between the cracks, so this is not the perfect dichotomy of the types of models that one uses. And I want to talk a little bit about parameter-driven models, just kind of as a baseline as to what people do, and then I'm going to focus mainly on a class of observation-driven models, and I want to look at, what the advantages and disadvantages really of each, but then focus on the observation-driven models and the challenges that that one faces there. Okay, after this brief intro here, then we'll look at a class of nonlinear observation-driven models. I'll give you a warm-up example, which is like the integer Garch, in-Garch. I'll generalize this in-Garch. Often people assume that the count's conditional on some intensity is Poisson, but I'm going to generalize this to other discrete distributions and even any sort of non-negative valued random variable. So we can actually embed that in a one-parameter exponential family. I'll show you some examples. Ericsson stock, I like this one because the name sounds cool, returns of returns. Some goodness of fit. This is a grab bag of a bunch of stuff, actually. So we may not have a real theme here. And then some extensions. Extensions tend to be kind of tough, actually. The self-exciting threshold in-Garch model. Actually, this is not so hard, but that's an interesting example where you're not, you have different regimes that you can be in. And then the really hard problem is including covariates with these observation-driven models. It's not clear how to do it in a meaningful way. It's kind of a critical comment there. But we'll do it we'll make one attempt at it, and I'll I'll show you some examples. And I doubt I'll be able to go to multivariate, but we've looked at this in a multivariate setting. There's a lot of complications that one faces there. Okay, so let's talk about the starting point. I'll start with a sort of a Poisson example. In terms of notation, I'll have count data, y1 up to yn, so these are counts of n consecutive days or n consecutive observations of a time series. Some of the work I'll talk about today will include a regression or explanatory variable denoted by xt. This was our main motivation, is that we had count data and we wanted to build a model which had covariates. And the question was just how to do that. And one kind of simple way to do that is just to use the kind of Poisson regression, sort of extend the notions of Poisson regression. So we'll think about the distribution of yt given this covariate vector and some stochastic process, which we'll call alpha t, is the yt's given this, the xt's and alpha t they'll be independent and they'll be Poisson. And we use a log link here, so the mean mu t of this Poisson variable given the other components will be xt transpose beta, and then you'll have this alpha t, the stochastic process there. If we didn't have this alpha t here, if that alpha t was 0, then this would correspond to just the standard Poisson regression model. So it'd be fall into the kind of a GLIM setting here. But we want to model the temporal dependence through this stochastic process alpha t. And that's sort of the key piece, is how do you model this alpha t. The primary goal, initially anyway, in this 20 years ago or whatever, was really making credible inferences about beta. If you didn't have this alpha t there, then it's not clear that your inferences about beta would be legitimate, in the sense that you don't really believe that this is exactly right. You haven't modeled the temporal dependence. So, so this alpha t, the way we view it in time series and in statistics in general, is that this kind of sops up what you don't include in the model. You don't know exactly what covariates. Obviously, you're going to exclude maybe some important covariates, or you've included some that you should not have. And so this is kind of correcting for your mistakes and maybe misspecifying the model here. But you could probably still make reasonable inferences about beta if you model this alpha t correctly. So I'd like to think of this alpha t as sort of the Rumsfeld variable. Rumsfeld was the, maybe this is a dated analogy, was the Secretary of Defense for Bush for a while. And he had this great expression about there are known knowns and known unknowns, and then I can't remember what the last one, unknown, whatever, unknown unknowns or whatever. So this is what I think of. We put everything there. The known unknowns is kind of, that's the alpha t term that sops it up. Okay, so that's sort of the kind of the framework which we started with. And a parameter-driven specification means that this alpha t is just, it's going to have its own probabilistic mechanism that it follows. So in this particular example, I want to think about alpha t as being an AR1 process. Okay, so here's alpha t is going to be stationary Gaussian AR1, so we'll make it Gaussian. And I've written in this strange way, I made it have mean minus sigma squared over 2, and the variance of the noise term that drives this AR1 is going to have variance sigma squared times 1 minus v squared. The reason for that is then the variance of this alpha t process is sigma squared, so it's just a way to standardize it. And the reason why I put this mean minus sigma squared over 2 will be apparent in a couple lines. So what are the advantages of a model like this? I mean, I just chose this AR1, I mean, there's other models that one could choose there. What's nice about it is that this, the process YT inherits the stability properties from this latent process, if you want to call it, think of alpha T as a latent process. So in particular, you'll have ergodicity and mixing. These are easy to derive. So in particular, you have strong mixing at some geometric rate here. You'll also have it for the YTs. So it's a very nice property to have, especially when it comes to the inference setting. I should be a little bit careful about XT transpose beta. That would be true for if this was just a constant. But the other aspect about this model is that you have, you can interpret the regression parameters in a nice way. So if you look at the unconditional mean, you'll get this, this term coming out, and then you'll get the expected value of e to the alpha t. And when you compute this expected value of e to the alpha t, the way I've set this up with mean minus sigma squared over 2 and variance sigma squared is that the mean of this guy is actually 1. So in fact, that this is really what you'd like to have when you do Poisson regression, is to have, at least on the log scale, it's linear. Okay, so you could think of the conditional mean on a log scale. It's a linear, it's a time series model with a regression component. So those are the advantages of this parameter-driven model. Some of the disadvantages, well, one of the big disadvantages is that estimation is difficult. So this is typical with these sorts of models. This is very similar to stochastic volatility process, except the conditional distribution here is Poisson instead of, say, Gaussian or T. So estimation tends to be difficult. There are some strategies that one could use, which I'm sure most of you are probably more familiar with than I am. Composite likelihood is one approach that we've used, and it's somewhat promising, I think. The problem with because the estimation is difficult, model building can be laborious because you want to try different covariates and stuff. It's not like you just do it one time and you're done with it. So this can be a problem because, especially in time series, you never know what lags to include for the covariates and how to adjust them and that sort of thing. So this model building thing is a non-trivial aspect, especially when the estimation is difficult. And then prediction is a bit more difficult as well. So you can't do these things in closed form. You have to rely typically on simulation methods. So it has some great advantages. It has some terrible disadvantages. The observation-driven models, and let me just introduce these with the same framework, is that the conditional distribution is Poisson. So we're going to assume here that YT, given this mean process, mu t or intensity, mu t is Poisson. And now I want to think about mu t as a function of previous observations. And I don't really want to bring in covariates here at the moment. So one of the nice features of this, and I'll give you an example, a fairly explicit one shortly, is that if mu t is an explicit function of previous observations, then you can calculate the likelihood. You just keep conditioning back. And so the likelihood you can calculate in a closed form, at least conditional on maybe the first observation or the first set of observations. So it has sort of like an AR, very, very close to an AR structure. Prediction is straightforward, at least one a lead time ahead. So that's a, and you can usually do the second one or more lags ahead as well. And what are the disadvantages of this observation-driven model? Well, stability behavior is more complicated. So when we would like to go to the inference stage, we say do maximum likelihood, whatever. We want to have consistency and asymptotic normality. So we're going to need some stability properties for the process. So in particular, stationarity is sort of nice, some ergodicity, and on top of that, we'll probably need something stronger, some sort of strong mixing-like condition in order to get some asymptotic normality. There's a chance you can use Martingale central limit theorems. Sometimes that works, but you still need, often you need pretty strong conditions on stationarity and ergodicity as well. And it's not so easy to incorporate covariates that are interpretable. It's easy to include them, in which they're not interpretable. Okay. So the two main theoretical issues that I want to talk about or address have to do with stability properties, existence of a unique stationary distribution. These are going to be set up using a Markov structure. So we'll need to come up with or establish a unique stationary distribution. In some of these models, we can prove the existence of a stationary one, but not necessarily uniqueness. In some cases, we really don't know the answer yet. And then geometric ergodicity, which will give us the right kind of mixing conditions that we want. Okay, so let me give you an example of a observation-driven model. This is called InGarch. I'm not sure who coined that expression, in for integer, and Garch, I'm sure you're familiar with Garch. One thing in time series is we can use a lot more acronyms. We're running short on them. That was a tongue-in-cheek remark. Okay, so here's an InGarch 1-1. So we'll have yt is the observation. Let's think of these as counts because they're supposed to be integer valued. And then given the past, ft minus 1 is the information set up to time t minus 1. Essentially, the past observations is going to be Poisson. And I guess I've changed from ut to lambda t. So that's the mean of the intensity function at time t. Okay, so that's the first part. And you can set a lot of this up just as like a state space equation. It's really nonlinear state space models. Here, the state, in a parameter driven, actually, I had a state space model, and the state equation was a linear time series model. Here, it's not going to be that. The state equation is going to have this form. It's lambda t is delta. Delta is a non-negative constant, plus alpha, lambda t minus 1 plus beta times y t minus 1. So if you were thinking Garch, the idea is that if you condition on the volatility process, then you have independence. And the Garch parameter, the volatility, the variance, sigma t squared, usually denoted that way, follows this linear relationship. So we can think of sigma t squared as some constant plus alpha times sigma t minus 1 squared plus it's usually beta times the return squared. So it's usually on the variance here. So this may say, okay, this is a bit of a stretch because we're not, this is a mean and this is the observation. But for Poisson, the mean and the variance are the same. So this is really the same actually as a Garch. It's identical. Okay, and so that's how this thing evolves. So if you want to go to, you want to generate the next observation from, you want to generate yt from the past, then you just calculate this lambda t, and then you generate a Poisson with mean lambda t, and you iterate that way. And so the question here is, when do you have a strictly stationary solution to these equations? So in terms of background on this model, it goes back a few years. Ryberg and Shepard considered this model, and they called it bin. And what they were thinking about is on the market, you bin, you buy and sell stocks or whatever, and then you bin the trades, the number of trades in a small time interval. So it was maybe like a 5-minute or 10-minute bin, and that's where this term comes from. And what they were modeling is both the number of trades and some time interval, as well as the kind of change in the value of the market. Oh, I guess I had it written right here. The number of trades in a small time interval, a time interval length of delta. And then Neil, they had established some weak stationarity, meaning on second order properties and that sort of thing. But that really is not what you needed. You needed sort of stationarity in the stronger sense, strict stationarity. And then, so I was talking to him about it, and I worked with a student, Sarah student of mine, Sarah Street, and we were able to develop some of the basic theory for this back in 2000 or whatever. And unfortunately, it was never published, although Sarah did she produced a PhD dissertation, and Neil was not quite finished with the piece on the economic application. He said to be a good econometrics paper, you have to really flesh out the econometrics. And so, unfortunately, it sat in a drawer, figuratively, and maybe literally too. It was unfortunate, actually, because it was nice. But what was interesting about this model is that we're looking at, think about the lambda t's. This is a Markov process, the lambda t's. Given the past of the lambdas, it only depends on the previous one, lambda t minus 1, because you're generating the conditional distribution of lambda t given the past is going to be Poisson. Well, it's going to be Poisson. You have a Poisson guy here, you multiply by beta, and then you add these guys there. It just depends on the last intensity. And the standard Markov chain theory does not apply to this model to establish the existence of a unique stationary distribution. So it was odd. And back then, I was reading a lot of mine and Tweedy, the book, and talking to Tweedy. And so, Richard is like the expert about stationarity. And I said, he was like, can you do this one? And he couldn't do it, which was strange. I mean, because he knew every trick in the book. He wrote the book, so he knew this. And then he says, why don't you look at chapter 6? I'm not sure if that was a chapter, but it was something, one of the later chapters. Look at that chapter 6. And there's something called E-chains in there. And he said, I've never used this, but there's some results in there on E-chains. And it turned out that the E-chains worked. So and he was excited because there was a nice application of using E-chains for something as simple as that. Okay. So in terms of properties of this in-Garch model, you have, these are Garch 1-1-like recursions for the intensity. I've already commented on that. In fact, the YT process, if you take YT and you subtract off lambda t, and then that's going to be so you're subtracting off the conditional expectation, then that's going to be a martingale difference sequence. And you can re-express YT turns out to be an ARMA 1-1 process, just like what you have for a regular Garch. But the noise here is going to be the martingale difference sequence. Driving it is going to be YT minus its conditional expectation, so it has a discrete, it'll be discrete. Okay. You can this captures positive serial dependence in the observations, positive serial correlation, in fact. That's what happens with these sort of Garch models. You have some over dispersion. The variance is greater than the mean, which is good because this count data, time series of counts, they tend to be over dispersed. And so we like to kind of remove that if we can. And then the parameter estimation really is pretty simple. You can write down the likelihood, at least conditional on the first value of the intensity. So there's some really nice properties about this. The theoretical developments, the way this went is with Sarah, she used E-chains to establish that thing has unique stationary distribution. More recently, Fokianis and others, what they did was they also kind of established a unique stationary distribution, but they kind of went through the back door in doing that. What they did was they added, if you added some continuous random variable to this equation, then you can use the standard Markov chain theory because you go from one state to anywhere else with a positive probability. And that's kind of a cheat, I thought. But in fact, we did that too in 2000 because I was trying to figure out a way around this. And so, but they did it in a more clever way than what we did it back then. So you add this perturbation and you make it phi irreducible. And then Neumann used a coupling technique to prove that this thing was beta mixing, and then more recently, when you bring Dukan into it, you're going to bring in tall weak dependence, and they were able to establish that. What bothered me about a lot of this was that the proofs kind of depend on this specific form, having a Poisson distribution, and you've changed that to negative binomial, you have to use a different technique. This was kind of a hassle, I thought. So I wanted sort of one way to, to cover all these different cases and to cover more general dependent structures, possibly. So let me first embed this in a more general framework. So here, I think about the observation equation that relates the state, which is, I called the intensity before in a Poisson case, lambda t, to the observation yt. So here, we'll think of something a little bit more general, is that we have the observation given some eta. Think of it as a parameter at the moment. This is going to be just one parameter exponential family. Eta is the natural parameter. And these are sort of the basic, it's a little review of the mean and the variance connections between these functions A. So the mean of y then is beta b of eta, which is the derivative of A, and then the variance is the second derivative of A, and the first derivative of B. B is a variant. B prime is a variance, so it means B is strictly increasing, so there's a one-to-one association between eta and B of eta. There's a nice property comes from this paper or you can generalize it from that, and it has some sort of stochastic bounded, or one's smaller than the other in a stochastic sense. Y prime is less than y double prime. We're thinking y prime has parameter eta prime, and y double prime has parameter eta double prime. If you have this relationship between the parameters, then you have one stochastically bounded by the other. And this last point is a key in applying some of the IRF theory. So IRF is iterative random functions. And the way, I'll tell you what those are. So the general formulation then is that we'll have this observation equation, which is yt given the past, is going to follow this one parameter exponential family, p of y given eta t, and then we'll have the state equation x of t. So this is like the lambda t for the Ingarch. So lambda t has been replaced by a Roman letter, xt for state, and it's going to be a function of the previous state and the previous observation. So if you think about that Ingarch, the xt, then this g function was just linear in x and y. This function g will satisfy these conditions. It'll be non-negative. We could put more states in here if you want to go back, but let's just do this one. We'll have a contraction condition. The contraction condition is that if you look at g at an xy and g at x prime y prime, the difference is less than or equal to a times the difference in x and b plus b times the difference in y's, where the a plus b has to be strictly less than 1. So that's the contraction condition that we'll assume about this on this g. So for the Poisson Ingarch, this g function, g of xy is delta plus alpha x plus beta y. Okay. For negative binomial, falls into this framework. Yt given ft minus 1. Here, the state we're going to have this will be this mean is r times 1 minus pt divided by pt, and then we're going to assume a linear structure here. I'm going to generalize this linear structure. I mean, it doesn't have to be. You can use other functions here besides this kind of function, but you need to have this contraction condition. So one easy function to use is this linear function in x and y. And again, alpha plus beta has to be less than 1. And here's an exponential autoregressive model that Fulcianus came up with that relates the current state to the previous state with some more nonlinear, in a more nonlinear way. And this also follows into the structure. And so, okay, so there's a bunch of different models that one could formulate where you specify this G, and when G's linear, that has this Ingarch style, but there are other ones too. Okay, so what is the method of proof? What do we use? What's the underlying theory that we're going to use to establish these stationarity and mixing? And Ben-Spear and I thought about this a long time ago, but we kind of dropped it. But it really falls naturally into this class of iterated random functions. It really is an iterated random function. That's the way these things kind of evolve in time. And so we're going to borrow from heavily from Diaconis and Friedman, mainly actually Wu and Shaw in 2004. It's a very nice paper. And the basic idea is that if the functions are contracting on average, then there should exist a unique stationary distribution. And then on top of that, it should be geometrically ergodic. So the way these iterative random functions are defined is we'll start with a family of Lipschitz functions, f of u. So it's being indexed by u, but you might as well think of this capital U as the unit interval, 0 to 1, because I'm going to draw, at some point I'm going to draw ID observations. You might as well draw ID uniform 0, 1. You can reduce it back to that. So we'll have on some complete separable metric space, this FU is going to be a Lipschitz function, and then we'll have some Lipschitz constant. Okay, and the way this Markov process is defined is you start with some initial state x0. The next random variable x1 is you take, well, let's say you take u1, u2 to be ID. Let's say it's just say uniform 0, 1. That's good enough probably. So you take x1 and then you choose you draw u1 and then you choose that family, that particular function, and then you evaluate it at x0. And you iterate, hence the name. X2, you do the same thing to x1, and you keep doing it. So you get a sequence of random variables like that. So at time n plus 1, it's just a composition of n plus 1 functions evaluated to the initial state of x0. And you define the backward process by just going backwards. So you just change the order of this, put fu n plus 1 and fu down there. And z, what you know right away is that these have the same distribution because the u's are ID. So it doesn't matter which order in which you do this. So this backward process, there's some results about this, is that it turns out that this guy converges almost surely to a random variable. Call it z infinity. And that, and because this guy converges, that means this guy must converge in distribution to the same guy, right? There's not an almost sure claim here, but it's just, it converges in distribution because these guys have the same distribution as that. Okay, so that's one remark, and that's how we're going to use this sort of result. And then many nonlinear time series have this particular form. You can actually express it this way, where xn is some function of xn minus 1, that's this guy here, and then of un, and then there's some parameter, will be a parameter of the model. So this fits into this framework quite nicely, I think. There's some other conditions on top of this. Let me just talk about the second one. This is geometric moment contraction. The first one is mainly an existence of a moment based on the metric. But what the second condition says that you start this chain at two different locations, x0 and x, and you iterate n times, and then you want to see how far apart they are based on how far apart the initial values were. Okay, and so you'll have the distance between these two, and then you can raise it to some power alpha. I mean, you can take alpha to be 1 if you wish. Then there's a constant which I've written this in a kind of awkward way, but there's a constant C and R which depend on alpha. But take alpha to be 1, say, and so you have a C and you have an R. And R is between 0 and 1, and this is R to some power n times the distance that these guys are apart. So you kind of have this geometric rate as to how fast these guys, xn of x and xn of x0 sort of forget the initial state. Then here's the theorem from the Wu and Shao paper, is that you get this convergence for every x in S, that the Zn of x converges to C infinity. This limit random variable is measurable relative to this ID sequence. And then this is really the key result, is that if you take x0, so it will turn out there's a stationary distribution then, one that has the existence of a stationary distribution. If you take x0 and x0 prime to be 2 independent random variables from that stationary distribution, you start these guys with 2 independent draws, and then you look at where you're at n time steps, and take the expectation of the distance that these guys are apart. This goes down like r to the n. So you have this geometric decay. And this will give you the enough power for the mixing via geometric array. Okay, so this first comment up here just says that we can embed our modeling formulation exactly into this. You just choose fu of x to be this function g of x. This is the function that relates the state at time t to time t plus 1. So it's a function of x, and then you take the inverse of a uniform, is f inverse of a uniform, and this is fx, which is the distribution of the yt minus 1. So this is how you get this function fu of x. And then this proposition here just says that everything holds, that the conditions of the previous theorem hold, so that you have what we need. So in particular, this xt is geometric moment contracting. Pi is it turns out pi is a unique stationary distribution. The yt is absolutely regular, so it's beta mixing, and here's the rate at this function goes to 0. And in particular, if you start this guy with the state with the stationary distribution, then the yt-xt pair is stationary and ergodic. Okay, so that's sort of the first result. So many of these models just can be embedded right here. So that's this remark. It says that I should read these slides maybe. I should click faster. So that's what this says, is that a lot of these things, models actually fit. The proof combines a special coupling technique and a geometric moment contraction property. So that's kind of a cool methodology. And then there's a comment I made earlier that often you can't use the phi reducible type Markov chain theory because these things don't satisfy that condition. Let's go into estimation. I see I'm chewing up time very quickly here. Go faster. Okay, maximum likelihood. So this function g now, we just add a parameter to it, so it may be d-dimensional. You have a true one. You can calculate likelihood. This is all really kind of routine. And here's log likelihood, the score function, and you get a maximum likelihood estimator by maximizing the likelihood. Now, we really wanted to give do the details in the proof. And that's always a little nasty, getting the right conditions, and I'm not sure these are the right conditions. So these are a bunch of regularity conditions that we needed, kind of standard in a way. So you have to, things have to be, the true value has to be in the interior. You have this other function, which I haven't talked about, has to be bounded below. It's like the XT's bounded below, but that was true because there was this delta parameter, so it's always greater than delta. You have to have some, in the case that the conditional distribution is a continuous one, then you have to have another condition on G. You have to have this kind of moment thing, and then there's this last one, A5, is an identifiability condition that you can distinguish between two different parameters. So the A0 through A5 are conditions you need to get consistency. So the maximum likelihood the estimator will converge almost surely to the true value. You need a little bit more to do the normality, so that's these two in red. So I do not want to talk about any more about that part. Here's the theorem. You have consistency, and then you have normality. Okay, so this linear dynamic model, it satisfies these conditions that you have this contraction condition on G. Okay, and so what you can do then, if you have this relationship between xt and xt minus 1, you can iterate backwards, re-express xt minus 1 in terms of xt minus 2 and yt minus 2. When you do that, that's kind of a typical time series exercise. You get xt theta as an explicit function of the past of all the yt's. It looks just like an AR1 filter applied to these OIs. So this was this function that I alluded to in one of the conditions for strong consistency of some properties about this as a function of theta. Here we can display theta explicitly. Theta consists of delta, alpha, and beta. So the maximum likelihood inference works for this guy. Here's the one which has some nonlinear dynamics. So we're using spline basis functions. So we keep the linear structure here, but we also add, we have some knots at location CK. You take the positive part and multiply times beta. And as long as this function is contracting, so there's some conditions on the betas together with the alpha and beta. As long as you have this sum being less than 1, then it's stationary and ergodic. So here's an example of this Ericsson stock. So this is actually like what Shepard had in mind. It's a number of transactions per minute for this Ericsson on a particular day. I don't really like this data set, but this is the one that's used in the literature. And here's the autocorrelation function for this particular data, and you can see the persistence doesn't go below that line for a long time. So we fit 5 different models to this data. We did a linear, and the nonlinear dynamics I'm thinking of with this basis spline structure. So we do both with Poisson, and we also do negative binomial, and then we also did that exponential one. I won't say much more about the exponential. And this red here is the intensity, the conditional expectation of y given the past. Let me just say a little bit about model assessment. So this is a short interlude of how you might check model fit. You could use a standardized Pearson residuals where you take yt and you divide by you essentially turn them into martingale differences. So you could look at these guys. One thing that's used a lot now, in particular in time series, but also for discrete distributions, is that we're looking at predictive distributions, and we're looking at how we transform them back to uniform, and then we see how close they are to uniform distribution. And I like this a lot, actually. In the discrete case, there's a bit of a problem because of the jump over 1, so you can't take f of a discrete distribution and get uniform, but you can tweak it a bit. So there's Brockwell. This is little Brockwell. It's not so little. It's Junior Brockwell. It's Peter's son, and Chato and others have looked at this. So this is what you do. So I think you can figure this out with pencil and paper. And then there's some scoring methods that you want to assess prediction. I think Mark talked a little bit about scoring yesterday. I'm not sure if Peter did it or not, but here's some scoring things to assess how well these models are predicting. But I like the PIT one, this probability integral transform, because this really lets you know whether this model is doing the right job in prediction. I think it's a good way of looking at that. So when we do these PIT things and others as well, I like the plots on the left, the histograms. So when you convert it to this uniform in quotes, then you subdivide it into different deciles, and then you look at this histogram, and if it looks flat, that's good. And if it doesn't, it tells you where you go wrong. You have too many here in the tails, so it's not, you have more than what you should. So I think this is sometimes easier to interpret than the QQ plot, because it kind of depends on how you draw this line. And if you just look at these guys and see which one looks most like a uniform or flat across, then you immediately go to this one or this one. These are both negative binomial Ingarch as opposed to Poisson. So that seems pretty clear. This is one with linear dynamics, and this one has a nonlinear one knot, whatever. And if you look at the summary statistics for this, then you're led to the one knot negative binomial as being the best fit on all these different measures that we considered. So that was kind of nice. Here's another example that I liked because of the name, returns of returns. So here we're looking at daily price of Goldman Sachs from 1999 to March 2012. So we look at log returns, so these are the returns, and then I want to look at the times when the returns are outside a interval, and this is a big interval, outside the 0.05 to the 0.095 quantiles. And I'll look at return times for that. And so the tals are the times, hitting times, at which it falls outside this interval. And then we'll look at the times between. So why am I doing that? It's a good question. So the y tals then are the return times, the return to being in this extreme set, a rare set. If the log returns are really ID, then these yt's should be geometric. They should be ID geometric. And so that's what I really want us to look at does it follow a geometric distribution? And there's some earlier work by Chan and Gieman about this, where it turns out these were not geometric at all, which indicates some clustering in the data. And even when you go down to lower quantiles. So it's a measure of kind of extremal dependence in a way. And Thomas and Ivor and I looked at the same thing relative to something called an extremogram, where we can actually give confidence bands for this alleged geometric distribution. So here's the daily log returns of this Goldman Sachs. And then I'll put dots at the data that exceeds the 0.95 or is below the 0.05 quantiles. Those are the little circles. And just so that you understand what I'm talking about at the beginning, these colored dots are where you have these exceedances. So this would be tau 1, and then tau 2 is the next extreme point, and then tau 3 is the next extreme point, and tau 4, and so on. And then we're looking at the times between, the number of days between, you get this extreme set. Okay, so this is what the time series looks like of return times. And then this is the autocorrelation of that, so that if you're If it's small, if the return time is small, then it's likely the next return time is going to be small. Or alternatively, if the return time is long, then the next one may be long as well. This is a matchup against which should be a geometric distribution. The red is a geometric, and here's just the histogram of the return times. Of the return times. Return times of the returns. Okay, and it doesn't fit this geometric. So then we use these in-Garch models using negative binomial and actually geometric. So geometric fits into this family. And if you just look on the left-hand side and look at the one that's flat, that's most closest to uniform, it looks like this guy is the one. So this is a one knot with a conditional geometric distribution. And so it's a pretty good fit, actually. So okay, and so these are similar diagnostics to support what I just said. Okay, let me just do one other class of models, because these are kind of these are a fun class of models as well. So these are called self-excited threshold in-Garch, or just really expanding an acronym, set in-Garch. And the idea is you add a threshold to lambda t. Here we're going to think of Poisson. So we only did this for the Poisson case. Here, so what happens? So if the lambda t satisfies this recursion, if the previous observation was less than r, so r is some threshold, say it's like 5. So if r is less than or equal to 5, you satisfy this. And if y is greater than 5, then you satisfy a different set of recursions. And what's nice about this is it actually can capture negative dependence in the data. So you can get negative correlation. So what happens is, and the other thing that happens here is you don't need this restriction that the sum of these guys is less than 1. So as long as y is less than or equal to r, then you can relax this assumption that the sum is less than 1. They can be greater than 1. So it gives you explosive-like behavior. So when you get explosive-like behavior, eventually this yt is going to be large. It's going to be greater than r. When you're greater than r, then you'll have this contraction condition to bring it back in order to get a stationary solution. This is exactly like what happens for threshold AR1 models or AR models, the stuff that Tom works on. So here's the result that says that we still need this alpha 1 less than 1, but as long as this guy is less than 1, this is where you get extreme, you come back, then this Markov chain has a unique stationary distribution with moments of all orders. It has nice continuous, okay, and then you have things are ergodic and everything works out. This doesn't fall under this iterative random function suffer that we couldn't make it work. So the proof of this is actually using E-chains. So E-chains it comes back in this problem as well. We can do likelihood difference then, just like you might expect. In this case, we need a further condition that beta 1 is less than 1, but we don't really need the sum being less than 1. But we do conjecture that this is not really required, but in order for our proofs to go through, we require this. We have the consistency of the maximum likelihood estimators, we have asymptotic normality, and the rest of that. So I think this was kind of a fun set of examples. Extension 2 is including covariates. That's for the next time I come back to Cambridge. So I better end there, otherwise I'll go too long. So thank you for your attention.
For a couple of
Is there any interest in the explosive case, specifically when there's large beta, but without any thresholding, so it just really does explode?
I think in practice, I'm not sure about in practice so much. Maybe with if you're doing some sort of contagion or whatever with disease of that sort, that may go on. But you may not get stationarity.
I can't remember why he was interested, but it was.
Who was that?
Oh, some graduate student.
Oh, okay. Was
Just
interested
walked
in?
in my office and I didn't answer the question. That's why I'm asking you.
Okay. Let me think about it, and I'll get back to you. Yeah, I'm not sure. I mean, in account data, you don't really see that happening so much in the data. They're just, maybe you get 20 or that goes back to.
I think he was actually driving the Poisson process with an explosive Ornstein-Uhlenbeck process.
Okay.
But it should be about the same
Yeah.
kind of problem.
Yeah.
So another question, or maybe a remark. This last thing about the process having contractive properties when you're far away from zero, but not necessarily when you're close to zero. There's an argument by Lamperti that goes back many years about proving stationarity of some sort, where you have a potential function that only operates far away from the origin, and near the origin you don't try to specify anything. So it keeps you from wandering out to infinity.
Yeah.
And then there's a...
But this is kind of similar to the theory reducibility type conditions where they have some sort of contraction condition where on some set you have to have this nice behavior, and on a complement you can have wild behavior.
Hans Fulmer also wrote an article having a similar flavor,
Okay.
but it was a martingale type argument. And I forget what he actually, I forget exactly what he did, but it had
Yeah.
that flavor that when
Okay.
you were away from the origin, you had a super martingale structure pulling you back towards the
Yeah.
origin. And then when you
All
were
right.
near the origin, you couldn't jump arbitrarily far away from the origin in a single step, because
Mhm.
that could still screw you up. So you had bounded increments as far as you could jump away, and then you could prove things like stationarity.
Yeah, okay. Yeah, I haven't seen that, or the Lamperti one, yeah.
They're very old, like
Yeah.
me. That's what I know about them and you don't.
Yeah. I'm not going to touch that. Go there.
I have a question about the return series. If I understood that correctly, those were the extremes. You didn't take any gauge structure or anything into account. It was just the extremes, right?
Yeah, I didn't assume any underlying
Right.
model.
So if you do that after taking, say, a gauge model or something into account, and then take the extremes, taking the volatility process into account, does then the time series structure in this return of returns disappear, or is it still present?
I'm not sure if I completely understand your question, but let me answer a question I thought I heard. And that is, we know conditions about the underlying Garch process. So suppose it follows a Garch, and then we do what we do. Then does that process satisfy the conditions of our result of the return times being returns of the returns being what we needed would be mixing and that sort of thing. And I didn't do that sort of thing.
But it was much more
Okay.
basic. So because you have this volatility process, so you will have more extremes at the place with a high volatility, right?
Yeah.
And that may actually cause the effect of having this kind of
Exactly.
Right? So if you take this out by, say, filling a Garch model first and then take extremes in the residuals or something like that,
Yeah.
right?
Yeah.
And then do the same. Do you then still see?
Yeah, you do actually.
Okay.
Yeah, we've done that actually, where we've what I call is degarching.
Mm-hmm.
You degarch the time series, and then you do this thing that looks pretty close to geometric.
Tim gets the last question.
Right, this might be a silly question. Can you have multi-dimensional observations where there's dependence between two? Maybe you've got two stocks that are
Well,
interrelated.
That's like the last 3 pages of 3 slides.
Okay.
I don't want to show them. Well, I'll show them. I'll just, you turn think, you do the obvious sort of thing, but here's a bivariate one. And I'll just show you the structure of the Garch recursions now being a set of vector equations. Then there are conditions about the eigenvalues of these matrices and that sort of thing gets involved. What's more complicated here is how do you model the joint dependence? So for continuous random variables, it's a lot easier, but for Poisson ones, for example, it's not so clear how to do this. This is a bit old, and I've been working more recently on using a more general cupola to model that dependence, and which brings up another interesting issue about cupolas and discrete data, because discrete data may not uniquely determine the cupola, and so there are issues about identifiability and trying to do that, but yeah, we're kind of working on that aspect. But I think the time series structure actually saves us in terms of identification even with discrete data, because things bounce around enough that you can actually get some identifiability, which you don't get typically in the IID case.
Okay, well, let's thank Rich for a great talk.